Okay, so we're going to look at a specific example here. The fundamental, or the common way I'm going to write these equations is going to be something, in this case 1, times the t derivative of u, plus something, in this case 2, times the x derivative of u equals something, in this case 0. Now I'm viewing this as a transport equation, and as I derived it in the previous video, t is going to represent time and x represents space. And I didn't mention it in the previous video, but the reason we call this the transport equation is because it describes how something, wood chips or whatever, is being transported along a pipe or whatever is happening. Now, if we think about t as being a time variable, it makes sense to specify an initial condition, like an initial arrangement of the wood chips that are floating through the pipe, or an initial arrangement of the cars that are, going down the road, whatever it happens to be. In which case, I'm going to say u of x0 is equal to some given function f of x. Now, what I want to do here is, as I mentioned before, I want to think geometrically. And I want to think about this in the following way. I can rewrite that differential equation as the gradient of u dotted with the vector 2, 1, and that's equal to 0. Remember, the x vector comes first, the t comes second, but I write it with the t first and the x second just because that's kind of how we derived it. That's the format that we had it in. Okay, so what this is telling me is that the directional derivative of u in the direction of 2, 1 at any point is going to be equal to 0. So the directional derivative of u in the direction of 2, 1 at any point is going to be equal to 0. Because remember, this dotted with the unit, if I divide by the magnitude, if I divide by the square root of 5 here, this is exactly the directional derivative of u. Okay, so you don't need to have the exact directional derivative. We'll see as we go on. But what this means is that at any point, let's say I pick this generic point, I'm going to call it xt. What it means is that in the direction of 2, 1, so I'm going to go over 2, up 1, more or less. It means that in this direction here, at any point, u is constant. Its directional derivative in that direction is not changing. So what I'm going to do then is I'm going to think about a parameterization for all of the curves whose tangent vector is going to be equal to 2, 1. And if you're confused, just go with me for a little bit. So I'm going to get all of the curves of the form. So I'm going to use s as my parameterization variable. So we're going to have x of s, t of s is going to be equal to some x naught plus s, x naught plus 2s, t naught plus s. So for any x naught and t naught, what's going to happen here is I get the parameterization of a curve, then label my axes here in the xt plane, and its tangent vector is going to be equal to 2, 1. Now, because our solutions, our initial data here is on the x-axis, I'm only going to look at, so I'm going to get, if I choose all x naught and t naught, I'm going to parameterize the same curve over and over again. So what I'm going to do is I'm just going to look at curves where t naught is equal to 0. Okay. And this is going to give me all of the different parameterizations that sort of start on the x-axis when s is 0. So if this is my x naught here, it's going to start at the point x naught 0 when s is equal to 0, and as s increases, it's going to go on a line roughly like this. Okay, and if I have another x naught here, let me color code this a little bit better. And if I have another x naught, let's say here, the parameterization is going to go that way. Okay, now what I want to do is I want to look at the solution along each of these curves. So for a given parameterization, which like this parameterization depends on x naught, I'm going to say z of s is equal to u of x of s t of s. I'm going to say z of s is equal to u of x of s t of s. In other words, it's just the value of u along each one of these lines here. Okay, for each x naught, I'm going to get a different function. So I'm sort of fixing an x naught and looking at z along the line, but I'm doing this generically, so the argument works for all x naught. Now, by the by the multivariable chain rule, z prime of s is going to be equal to the x derivative of u. When I say the x derivative of u, I mean the derivative with respect to the first component, times x prime, that's x prime of s. I don't have enough room to write all of the arguments. And then plus the t derivative of u times t prime. Well, okay, let's think about this. X prime, this is my x of s, so x prime is 2. So this is 2 times the x derivative of u. T prime, this is my t of s, t prime is equal to 1. So this is just equal to the t derivative of u. Well, this is the left-hand side of the differential equation. 2 times the x derivative of u plus the t derivative of u is equal to 0. So what this tells us then is that along these curves, z prime is equal to 0. On this curve, z prime of s is equal to 0. So what this means, if the derivative of z is constant along this line, it just means z is equal to z of 0. But what is z of 0? Well, if you come over here and plug in s is equal to 0, it's just equal to z of u of x naught 0, which is f of x naught. So this is f of x naught. Okay, and then something similar is going to be true on this line right here. On this line right here, we know that z is equal to f of x naught. So on these lines right here, which we will see are called characteristics, on these lines, and they extend down here as well, but if we just think about positive values of time, we're only going to look at these parts right here. On these lines, or if you want to think about it, these rays, we know that the solution is going to be constant. So then the question is, given a generic point in the xt plane here, how can we figure out what the corresponding x naught is? So for example, if I start, let's look at a different characteristic just to get another example. If I look at a line like this, or a ray like this, again, these should all be parallel. I know they're not exactly. Let's say I take some generic point here. Actually, this might work a little bit better if I go the opposite direction. So if I start with a generic point, let's call it xt in the xt plane, I know that u of xt is just going to be equal to f of x naught, but I don't know what the corresponding x naught is. So I basically need to start here and draw a line. Geometrically, I need to start here and draw a line back down to the origin or back down to the x-axis and figure out what that x naught is. Algebraically, this amounts to solving the equations x equals x naught plus 2s and t is equal to s. I need to solve this for x naught in terms of x and t. Well, this is a system of algebraic equations. You do it whatever way you need to do it, but t is equal to s, so this is x naught plus 2t, and so we can see x naught is equal to x minus 2t. So x naught is equal to x minus 2t. And so what this tells us then is f of x naught, this is equal to f of x minus 2t. Okay, so in other words, xt was generic, and we just showed that u of xt is equal to f of x minus 2t, where f is our initial data. And I want you to take a minute to verify that f of x minus 2t, that u of xt defined this way, satisfies both of these conditions here, both the differential equation and the initial condition. Okay, but this is the basic idea. In the next video, I'm going to introduce a very generic, linear, first-order differential equation. I'm going to go over sort of the algorithm that we're going to use to find a solution, but it's going to be based on these geometric ideas right here I believe in the next video, at least I think in the next video, I think that in the next video it will be very generic and maybe a little bit confusing, but once we actually start to apply those steps to specific problems, I think it will become more and more clear what we're doing here. But I want you to always keep in mind these geometric ideas, and I'm going to reinforce those geometric ideas as we go along.